Welcome to the lecture number 2 on Galilean laws of motion by DHS Maithripala. In this lecture, I will be talking about the description of motion and the cause of motion as we see it. Or in other words, we will talk a little bit about conservation of something called linear momentum and its consequences. So first, let us look at how to describe motion. So what are the things that you need to mathematically or precisely describe motion? Let's, for example, think of a particle moving along a curve like this. So at time t, it will be at a position p of t. At a little time later, say t plus delta t, where delta t is a small time interval, the particle would be at a different point, p of t plus delta t. So the position of the particle at time p of t can be given by triple of numbers with respect to an orthonormal frame E1, E2, E3. And at a time t plus delta t, it will be given by the triple of numbers given by the column matrix X t of plus delta t, again giving the distances along each axis to the point P. Now, since these are ordered triple numbers, or if you may think of it as column matrices, you can take the difference between the two. So if you take the difference between the two and divide by delta t and take the limit as delta t goes to 0, you get another 3 new numbers. So in calculus, what that means is it is just basically the element by element differentiation of x of t as a function of t. So x1 dot and x2 dot and x3 dot. So here the dot means the derivative with respect to time t. So if you again look at this from a geometric point of view, you notice that xt delta t minus xt is this line segment in a frame that is situated at P but parallel to E. So parallel to E, situated at P, and this line segment will have the representation xt plus delta t minus xt. Now, as delta t becomes 0, what happens to this line segment? This line segment approaches the tangent to the curve at point P. So this x of dot is simply the tangent to the curve at point P. And we will call that the velocity of the point P in the frame E. The magnitude of the velocity given by the Euclidean norm, or this thing explicitly, will be called the magnitude of the velocity. Similarly, once you can again differentiate this or take the derivative of the difference between this quantity at t plus delta t and this quantity at t and divide by delta t and take the limit delta t goes to 0, you get another 3 numbers, x1 double dot, x2 double dot and x3 double dot, and we will call those the accelerations of the point P with respect to the frame E1, E2, E3. Now, if you notice P, the representation of the point P, of the point at time t given by x of t explicitly depends on the frame. So if you change the origin or if you change the orientation, these 3 numbers will change. And similarly, the velocity will also change. So the velocity and the position representation of the point particle explicitly depends on the frame. Now, if you have 2 inertial observers, we have seen that 2 inertial observers are related by the fact that their 2 frames are moving with respect to each other at constant velocity. Therefore, it is easy to see that actually the acceleration represented in both inertial frames will be the same. So even though the velocity and the position are different for 2 inertial observers, the acceleration measured or represented using 2 inertial observer frames will be the same for any 2 inertial observers. So what governs the laws of motion? What we observe is if you throw a ball at a certain velocity in a certain direction at a certain angle, it will always go the same distance during the same time interval if there are no other disturbances. Well, let's say if you do this experiment in a very room that does not have a blowing or a draft, then if you repeat this experiment over and over again, you will find that the ball will go and land exactly at the same place and if you repeat the experiment exactly the same way. So Galileo LD this thought experiment and he came to the following conclusion. He said, and he actually noticed that if you are inside a ship and the ship is traveling at a constant velocity v, whatever you do inside the ship, a pendulum, throw a ball, or drop a ball, whatever you do, there is no way that you can figure out whether the ship is moving at a constant velocity v or is standing still. So he concluded by saying that, therefore, all laws of motion must be inertial observer invariant. Why? Because inertial observers are the ones who are traveling at constant velocity or are traveling at constant velocity with respect to each other. So if you cannot discern whether you are standing still or moving at constant velocity with respect to other frames, both, and there's no way of doing any experiment to figure out which is which, then all laws of motion must be the same for all inertial observers. So he also did a lot of experiments where he would draw these balls of different sizes or different make, and measure the time that it takes to fall from the tower, and so on, and also roll very smooth metal balls of various types and sizes along inclined planes like this, and also collide different balls of different shapes, sizes and shapes against each other, and he observed this, what was happening. So he would make measurements as to the time it would take for a particle or any of these objects to move a certain distance, and so on. And he came to the following conclusion. So he noticed that there was some property of the system of interacting stuff that seemed to be conserved. So in this example, if you notice, when this travels and hits, it comes to a still, and that moves with the same velocity. Now this hits and this comes to gauge that velocity, and this becomes standing still. So well, in a modern day, you can do this similar experiment by throwing tennis balls together in the International Space Station, and you notice that something seems to be conserved. And what is that? So what Galileo Galilei concluded, and we will actually summarize in a little bit of more modern way, is the following. So that these are what we call the Galilean laws of mechanics. Everything is made up of particles. So this was not actually thought of at the time of Galileo Galilei, but now we know that everything is made up of particles. So object is a collection of particles. And so these objects are made up of particles. If they're made up of particles, they interact with each other. They must interact with each other. And they also have, each particle will have a unique property called mass that is the same for all inertial observers. So again, to recall, two inertial observers are related by these following relationships, or in other words, their frames are moving at constant velocity with respect to each other without rotation. And so each particle has a unique property called mass that is the same for all inertial observers. So if you multiply the velocity by the mass, you define something called the momentum. So what Galileo Galilei through these experiments found is that the momentum obviously does not depend on is not independent of the initial observers, because the velocity is not independent of the inertial observers, even though the mass is independent of the inertial observers. So the momentum is not an inertial observer independent quantity, but what he observed is, through those experiments and what we saw in the previous videos, is that all particles interact. So all particles of the tennis ball, all particles in those billiard balls, all of them interact with each other in such a way that the total sum of linear momentum of all the particles remain constant. So he made this profound conclusion that through all this experiment, that every particle has a unique property called mass, and if you multiply the mass by the velocity, you get momentum. You add all the momentum of all the interacting particles or objects together, they always seem to be constant. And that this conclusion, all inertial observers would agree upon. So all inertial observers would agree that the linear momentum, as they measure in their own frames, is always conserved for a set of interacting particles. So let's next look at a few consequences of this profound observation of how the universe works, namely that all particles interact with each other so that the linear momentum is constant. So let's take a set of particles, discrete set of particles. You may think of tennis balls, n number of tennis balls, add their momentums together. So that is velocity times their mass. And so it is constant. That's what the conservation of linear momentum says. Now this constant is not the same for each different inertial observed. Why? Because this is not the same for all inertial observers. So this constant, though all inertial observers agree that the total momentum is constant, what that constant will be different from inertial observer to inertial observer. So easy way of making that quantity also the same would be to actually differentiate both sides. Then you will get something like this. So a direct consequence of the conservation of linear momentum is that if you differentiate the momentum or the total rate of change of momentum of a set of isolated particles is zero. So you have a set of particles that are only interacting with each other and not with the rest of the universe, so isolated from the universe. And if you add the mi times xi double dot of all those particles, that sum should be zero. Or in other words, the total rate of change of momentum is zero. Now, what does this say? So let's isolate only one of the particles in this summation. In this summation, let's isolate the ith particle and take all the other particles or all the other terms in the sum onto the right hand side. So that's what we have done. Now we will call all these other things Fi. So what is Fi? Fi is the influence of all the other particles on I. Influence of all the other particles on I. We will call that Fi. Now that Fi is what we call the force. So the force is nothing but particles interacting with each other. So we have seen that all particles interact with each other in such a way that the linear momentum is constant. Now, if you isolate one particle and look at the influence of all the other particles on that, what you notice is mi times xi double dot is equal to that influence. In other words, simply the summation of all these terms. And that is what we call the force, and that gives you what we know as the Newton's second law of motion. Now, if you restrict this to only one particle, if there was only one particle in the summation, what do you get? Mi xi double dot is zero. So what's that? What that says that every particle isolated with the rest of the universe, or is the only particle in the universe, then it has to be either standing still or moving in a straight line with respect to the inertial frame that we are talking. That's Newton's first law. Now let's think of what happens if you had two particles. So if you had two particles, what would happen? N is equal to 2. So if N is equal to 2, you would have one particle mi xi double dot is equal to minus mj xj double dot. So but mi xi double dot is equal to the force acting on I, as this definition, due to particle j. And then what is this? So what does this tell you? This tells you that the force acting on I due to j is the minus of the force acting on j due to I. And that is nothing but the Newton's third law. So Newton's first law, second law, and third law are seen to be nicely a consequence of the conservation of linear momentum. So let's be a little more precise and define or summarize what we have talked about so far. Forces arise only due to particle interactions, and the force is an inertial observed invariant property. Why? Because that law holds in all inertial frames. And there are only 4 types of known forces or interactions: gravity, electromagnetic, weak interactions, and electromagnetic strong nuclear interaction. So if you just look at one particle and search for all these other interactions between particles and replace that with what we call the force, you get Newton's equations. Mx double dot is equal to force, or m times acceleration is equal to force, or the rate of change of momentum is force. Now let's look at a few more consequences of this conservation of linear momentum. Think of a set of particles isolated inside a box. So the box also has particles. All of these are isolated from the rest of the universe. Or in other words, the interactions with the rest of the universe are very small, so that interactions can be neglected. Let's look at what happens to this set of particles. Let's first find the center of mass of all these interacting particles. So this is the expression for the center of mass, MIXI, Sol summation divided by the total mass summation of MI. Now, if you differentiate this, we get this. And so the conservation of linear momentum tells you that since all these particles are isolated from the rest of the universe, but are interacting with each other, their total momentum must be constant. So what does this tell you? This tells you that the center of mass of all the set of particles is always moving at a constant velocity. So if you have a set of interacting particles, irrespective of how they are behaving inside, you would observe that if you try to keep track of its center of mass is either moving in a straight line, or is remaining at rest, or is moving at a straight line in a constant velocity. So all inertial observers agree that the center of mass of isolated but mutually interacting set of particles is moving at a constant speed of light. So isn't that fantastic? That's one of the very easily obtainable consequences of the conservation of linear momentum. So you see this actually in this experiment. So this is a water ball in space, in the International Space Station, and so all these water particles. So this bubble is made up of a lot of 10 to the power 23 order of water particles. So the particles are moving inside. However, the center of mass, if you keep track of it, it is moving like mx double dot is equal to 0. Why? Because in the outer space, the gravity is very small and can be neglected and can be thought to be zero. So though the particles are moving inside, the center of mass behaves this way. So this is again a direct consequence of the conservation of linear momentum. You see that a little more clearly over here, where this guy now is actually injecting some dye into the water bubble. So moment you inject the dye into that, you see that it diffuses all over the water bubble. So what that tells you is that there's internal motion of the particles inside. But if you just keep track of the center of mass, that is behaving like mx double dot is equal to 0. So let's again take a closer look at linear momentum of a set of particles. Consider a set of externally and internally interacting particles. So before we only sort of looked at a set of interacting particles that were isolated from the rest of the universe. Now we will have a set of particles that we are interested in. So these particles are interacting with each other as well as with the rest of the universe. So we will break. So we'll look at one particular particle, ith particle, and write down the rate of change of momentum. We saw that from the Newton's second law, it is equal to the force. So we'll break that force into several parts. One is the force acting on that particle due to the interactions with the rest of the world, not with the particles itself. And the other one due to the interaction that I feels due to the jth particle and summed over all the other particles. So in other words, this is the internal particle interactions, the force due to internal particle interactions, and this is the force acting on the ith particle due to the external interactions with the universe. Since we saw that Newton's equation, Newton's third law or conservation of linear momentum tells you that all particle interactions are equal and opposite. When you take them pairwise, this summation will be 0. When you sum it over all particles. So when you get the total rate of change of momentum of all the particles, this summation will vanish. Why? Because Fji is equal to minus Fij, and you will get the total rate of change of momentum of all the particles is equal to the summation of all the external interaction forces acting on the particle. So P dot is equal to Fa. So this is another consequence of the conservation of linear momentum. And we will call Fe, or the summation of all the external forces acting on the particles, to be the resultant of the external force. Again, if you write this thing in terms of the center of mass of the particles, we get a very nice relationship that mx double dot is equal to the rate of change of the total resultant external forces acting on the particle. So like in that water bubble, so if you keep the water, if you drop this water bubble on Earth, this is exactly how it would behave, like in space, but only difference is it would fall down to Earth because of the gravitational force, external gravitational force acting on all the particles. So the interaction between Earth and the particles the resultant of that will be for that water bubble to fall down to Earth as one single bubble. And we see that actually in raindrops. Let us define a new quantity called angular momentum of a particle P of mass m. This is very closely related to linear momentum, and it is defined as follows. So if xi is a representation of the point P in the frame E, which is ordered triple numbers or a column matrix, and if O is the representation of the point O prime with respect to the frame E, and again it's ordered triple numbers or a column matrix, and if you take the difference between xi minus O, now that can be done because it is an element in R3, and you get another ordered triple of numbers, and what that ordered triple of numbers gives you is this line segment with respect to a frame that is parallel to E but situated at O prime. Now if you get that R3 element, which is this ordered triple of numbers, and get the cross product with the ordered triple of numbers that give you the linear momentum of the particle P, or mi times xi dot, and that is what we will define to be the angular momentum of the point P in the frame E with respect to the point O prime. Now if you differentiate that, you will get this expression over here, and this thing comes from differentiating this term over here, and from this term you have mi xi double dot. So mi xi double dot is equal to the forces acting on the particle I due to the interactions that it has with all the other particles in the universe. And now this term we will call the moment of that force Fi about the point O prime in the frame E. So moment of the force Fi about O prime. If O prime and O are the same, if this is the same as that, or in other words, if you take the angular momentum with respect to the origin of the frame, we get a simple relationship that says the rate of change of angular momentum is equal to the moment of the force about the origin of the frame. And this is very similar to the linear momentum case, where the rate of change of linear momentum of particle is equal to the forces acting on the particle. Now let's look at a collection of set of particles and the angular momentum of this total collection of particles. So this is the angular momentum of a isolated particle, one particle. This is the rate of change of that particle, the angular momentum of that particle for the point O prime. And this is the moment of the forces acting on that particle about the point O prime. Now let's add all of them together for all the particles, the set of interacting particles in the system. So we have a set of interacting particles. They also interact with the external particles in the universe. And so we'll only look at this set of specific particles that we will call the system of interacting particles. So let's add all the angular momentum of all the particles in the system. And we will call that the total angular momentum of the set of particles about the point O prime in the frame E. And that will be just summing this thing over, will be given by this expression over here. Now we will break this the forces or the interaction forces acting on the ith particle into two parts. Interaction forces due to the particles in the system itself, or the internal interactions, and the interactions due to the external particles of the system, the particles that are outside the system or the rest of the universe. So we will break this term into two terms. Now the third law of Newton's equation, which is also a consequence of linear momentum, tells us that the particle interactions are equal and opposite. Now if additionally you assume that these particle interaction. So when a particle I interacts with particle J, their interactions are equal and opposite. But if you assume that those interactions are along the line that joins the two particles, because there's no other preferred direction other than that, and then if you do that, then what we will notice is this term goes to zero, or the total force moment due to all the interaction particles will be zero. Now, if you substitute that, what we get is the total angular momentum of all the set of particles is given by this expression over here. So you just do the bookkeeping, substitute for the center of mass expression, you get this thing over here. And where tau E is the resultant of all the external force moments acting on the particle about the point O prime. So if O prime happens to be the center of mass of all those collection of particles, then O will be X bar, O will be X bar, and we get a simple relationship that is similar to what we got for the rate of change of total linear moment. So if we take the force moments and the angular moment with respect to the center of mass with a collection of particles, then we find that the total rate of change of angular momentum is equal to the total force moment of the external forces acting on the system of particles. So again, if we summarize this, so we had for linear momentum a similar result. The total rate of change of linear momentum of a set of particles is equal to the resultant of the forces acting, external forces acting on the particles. And this also gives you Newton's equation that tells you the mass times the center of mass acceleration is equal to the force, because this is equal to that. So the center of mass, so you have a collection of particles, but the center of mass looks as if all the masses of the particles, the total mass of the set of particles is concentrated at the center of mass. So the center of mass behaves as if the resultant mass is concentrated at that point, and all the resultant forces are also acting at that point. Now you have a similar result for angular momentum. If you take the moments above the center of mass, then the total rate of change of angular momentum about the center of mass is equal to the resultant of the moments due to this external forces, also again about the center of mass. So we have these relationships. So this is the total linear momentum of the set of particles. This is the total angular momentum of the set of particles. This is the total external forces, resultant external forces acting on the set of particles. This is the total resultant force moments of the external force moments acting on the particles. And if you restrict it to isolated set of particles, then this is equal to zero and that is equal to zero. And we recover the following relationship. A restatement that all the particles interact in such a way that the linear momentum is conserved. And particles are equal and opposite. And additionally, particles are pairwise interactions are along the line joining the particles will give us that the total rate of change of angular momentum is also constant. So again, this is not this is a direct consequence of that, but we will find that this expression turns out to be very useful when we treat bodies where the distance between any two particles remain fixed or rigid body. I will conclude this lecture by defining a new quantity called kinetic energy. It is simply defined to be the Euclidean norm squared of the velocity times the mass times 1/2. So if you notice, the velocity, since it is not an inertial observed invariant quantity, the kinetic energy is also not an inertial observed invariant quantity. So two different inertial observers will measure the kinetic energy of the same particle to be two different quantities. If you differentiate the kinetic energy with respect to time, you get this expression over here. This can be easily verified. And I invite you guys to try it at the end of this lecture. And if you take mi xi double dot, you find that that is equal to the force acting on the particle. And now if you look at this quantity and integrate it from T1 to T2, that is what is typically defined to be the work done by the force. So what this tells you is that the rate of change of kinetic energy is equal to the power or the force times velocity acting on the particle.